In this video, we'll begin our discussion of simple linear regression, the first regression topic that we'll cover in this course. To start, we'll review a couple of different basic kinds of relationships that variables can have. The first type of relationship that two variables can have is something called a functional relationship. This kind of relationship is analogous to, say, the conversion between Fahrenheit and Celsius degrees. If we have a degrees in Fahrenheit and wish to convert those degrees to Celsius, there is a simple equation that we type our numbers into. It works every time. There is no variation in the result. The number will come out to be the exact same every time we run that equation. This type of functional relationship is very useful, and you can think of it as it's heavily used in mathematics and a whole bunch of different other areas. These tend to be theoretical relationships that we hypothesize and assume are true. Very often in physics, sciences, etc., and again mathematics, we'll see these types of functional relationships. The other type of relationship, and one that we'll focus on in this course, we'll call a statistical relationship. Statistical relationships are not necessarily perfect relationships. That is, if I use one variable to try to determine the value of another variable, it won't be right every single time, as it would be if I'm trying to use the Fahrenheit value to calculate the Celsius value. In fact, sometimes our guesses can be dead wrong, and it's important to know just how wrong we can be. Quickly, we can illustrate these types of relationships in a graphic. Let me pull one up. This graphic illustrates a functional relationship and a statistical relationship. In the functional relationship, you can see that every point lies exactly on the predicted line. Again, this is the same as the degree transformation from Fahrenheit to Celsius, as if I'm moving from a Fahrenheit value to a Celsius value, that Celsius value can be predicted by a linear equation. In a statistical relationship, though, we hypothesize an underlying pattern that tends to be true or tends to describe some of the variability in the data, but that isn't true for every individual person. So in this particular case, for every single degree that I convert, every single one falls along this line. However, in the second case, for every single person I'm trying to guess the value of, or widget, anything, I'm saying person because I study people typically, but we can have any data point. For any data point I'm trying to guess the value of, the data point may be on the line, it may be very far off the line, but hopefully these data points tend to fall onto the line. Now, the line that we create in statistical relationships is intended to address an underlying relationship, and we use data that we collect to address that underlying relationship, assuming that there's some amount of error in that data. Because of this, though, and because our data aren't necessarily representative of the entire population of data, we may have a best guess that isn't quite correct. This is shown in our third graphic, where we can see that our best guess, this black line, is slightly different than the true underlying relationship that generated these random data, the green line. What you'll notice in this particular case is that though the black line and the green line are separate, and we can see that they're distinct, they're very, very close. And this is the goal of our statistical model, is to use observed data to guess at an underlying relationship that is true for the population. In this case, with 50 data points, we gathered a pretty darn good estimate of this dark green dotted line, which is the pattern for an infinite number of data points. So, why use simple linear regression? And I am going to use the acronym SLR pretty often to stand for simple linear regression. So when you see SLR, think simple linear regression. There are two main reasons why we use simple linear regression. We use it to describe, or descriptively. This describes the relationships among data. and how different variables can relate to one another. So this is the first reason we would use simple linear regression. A second reason that's very common is prediction. We want to predict future values. Think if we could predict the stock market tomorrow, we would know if we need to go out and spend our life savings to buy a whole bunch of stock, or if we need to sell everything because the market's about to crash. If we could predict that future value, we would be able to make a lot of money. But there's also a lot of things that we could do that would be more altruistic. We could help people by incorporating more and better pharmaceutical products. We could be able to predict weather patterns to allow others to know when it's going to be a bad year for bugs, if there's a higher fire risk this year, a better predicted crop output to determine food stability in regions where food is not always accessible, etc. This idea of prediction is extremely important, and you'll hear of methods like cross-validation, and I'm just going to mention lasso here because it's on my mind, but there are many methods that you can do to get more and more accurate prediction. This said, in research, we often look descriptively at problems to determine what variables are actually related to the outcome. Prediction may be related in the sense that in the prediction we're using whatever we can to get the most accurate determination of the outcome, but in prediction we don't particularly care about the relationships between any variables so long as we can predict accurately. In descriptive linear regression, we're really looking to describe and determine what the relationships among variables are. Goes without saying, these goals are very different and can have very different purposes and very different methods that we use to meet them. Typically, I will use both, actually, depending on the type of problem I'm looking at. Perhaps more commonly, because I'm involved with research so heavily, I use descriptive, not descriptive statistics, but a descriptive approach with simple linear regression where I'm determining relationships among variables inferentially as opposed to trying to predict a future outcome. Now, all of this work depends on having valid statistical models. So first, we should talk about what is a statistical model. A statistical model allows us to assess data that are too complex for us to understand. Thinking about this, if I handed you an entire data sheet, you may not be able to look at all of the X and Y coordinates and then walk away with a meaningful understanding of what all of these data mean. Statistical models simplify this information. So we first simplify the information into a summary and then interpret the summaries. So for instance, graphically, you can see that we took the data points. Instead of leaving them as data points, we simplified them into a single line, which is something that we can understand with just a slope and an intercept. So we took 50 numbers and we reduced them to 2 numbers, a slope and an intercept. And then we can interpret those slopes and intercepts. This is a great example of what a statistical model does. And using a single line, and is our first and probably most basic statistical model that we'll discuss. One of the reasons that I like this so much is because it provides a nice visual, which isn't always possible. Another way you can think of this is as a toy car. Let's say a toy Ferrari. This may allow us to study features of a larger and more complex reality that we may not have access to. And you'll find that data access is very important. If we don't have access to the entire world of data, then we can't make claims on the entire world. However, if we have access to a smaller part or something that's smaller, it still models, it still looks like a Ferrari in this case, we can use that to maybe draw some conclusions about what the bigger item has. So for instance, we may take our toy car and determine that a real Ferrari has 4 wheels, or determine the basic shape of a real Ferrari. Thinking about this line, we may determine that the data in reality tend to go up. As x increases, y tends to increase in a positive relationship. So in this particular case, again, we're not modeling all of the complexity of the data, but we are getting some big picture ideas that come from our simplified statistical model. A valid statistical model is one where the concept, conclusions, and measurements are all well-founded. And if you think about this as the line we were looking at earlier, you can think that the line works well. The line fits the data very well. So for instance, if we had someone who handed us what they called a toy Ferrari, but it looked much more like a motorcycle, then we would have a problem because our line or our model wouldn't fit reality very well. So let's say somebody made a statistical model, and instead of the line going from the bottom left to the top right, the line went from the top left to the bottom right. In that particular case, that statistical model wouldn't model the data very well, because in this particular case, the data seemed to be going from the bottom left to the top right. Also consider, let's say we had a line that went from the bottom left to the top right, but let's say instead of being between x and 0 to 10, it was from x from 100,000 to 110,000. Even though the general pattern might be the same, it may not fit this data particularly well because of the location of the model. More complex statistics that we'll cover later in the course allow us to more validly model more complex situations. So for instance, if I'm dealing with a more complex situation that maybe can be described by a simple line, more complex statistics can allow me to model that. However, these can add complexity to the interpretation. The balance between interpretability and validity can sometimes be hard to find. So in this particular case, when we're looking at a particular model, we want to be able to interpret it. For more complex situations, though, we need complex statistics to be able to interpret that. However, complex statistics make interpretation harder. So we strike this fine balance where statistical models are intended to make easier things to understand. But then if we make our models too complex, we can't understand even our model. So we need to find a way in which we can keep our model as simple as possible. Sometimes this is called the law of parsimony. It wouldn't be a good statistics course unless I talked a little bit about causality. I'm sure you've heard this before, but correlation is not causation. What this ends up meaning is that the relationship between two variables does not mean that one variable causes another. So for instance, in the previous course, we looked at the relationship between balance and strength. We noticed that there was no real relationship between balance and strength, but if there was, it wouldn't mean that balance causes strength, or strength causes balance. Note that these things can be true. All that we're saying is that a statistically significant correlation does not necessarily mean that there's a causation. Note that it is not the statistic that determines causation, but the study design. In fact, the statistic or correlation and causation is often the same. So when we talk about causation, we're not talking about doing a different computation. Oh, if only you did a causation calculation instead of a correlation calculation. That's not how this works. How it actually works is that when we're looking at a particular relationship, depending on how we set up the study to assess that relationship, that study design is what determines whether or not we can make a causal claim. We aren't going to go too much into this. You can take another class that we offer here called Experimental Design to learn a bit more about how these separate out. But broadly, study designs can fall into two large categories: observational studies and experimental studies. Real quick, I want you to think of an example. This is one of my favorite examples, so if you've been in my class, you've probably heard this before. This is ice cream sales and shark attacks. So if we look at raw data, if we didn't do anything else but just observed the data, this would be an observational study, we would notice a reasonably high correlation between ice cream sales and shark attacks. Now, because we're good statisticians, we remember correlation is not causation. That is, that just because these two variables are related in an observational study, that does not give us enough information to determine that one causes the other. And think about what that would mean. Does ice cream sales cause shark attacks? That is, if I go out and buy an ice cream, or do sharks just love ice cream so much that they just want to gnaw it out of you? No, that's probably not true. Do shark attacks cause ice cream sales? After an individual witnesses a shark attack, does everybody just say, man, I've got a hankering for ice cream right now? Well, no, that's probably not true either. It could be the case that some underlying variable causes them both. Let's consider a variable like season of the year, where in winter we may not have very many ice cream sales and we may not have very many shark attacks. And in the summer, we may have lots of ice cream sales and lots of shark attacks. This is just one risk, and we won't go into all of these, but one risk as to why correlation in an observational study can't be used to claim causal relationships or causation. Now, we could design an experiment. It wouldn't be particularly ethical. What we would have to do is take, 100 different people, split them into two groups of 50, randomly assign people into each of these groups, drive them out into the middle of the ocean, and just stuff a gallon of ice cream down the throats of half of the people and then toss them in the water and see who sharks attack. And if we found that sharks tend to attack the people who eat ice cream, we may say ice cream causes shark attacks. Now, that is highly, highly, highly unethical to do, so we would never actually do that, and I am, of course, completely joking when I recommend this, but it is what would be necessary in order to determine a causal claim. Note that the calculation of how we would look at these groups would be the same. We would still look at these relationships the same with the amount of ice cream and the amount of shark attacks and finding a relationship between those variables. All that would have changed is that instead of using an observational technique where I look at data that's been pre-collected, I would have to use an experimental technique where I design an experiment such that I can make causal claims. And with that, we are now finally able to get into the start of the real meat and potatoes of this class, simple linear regression. So real quick, let's start with the data requirements for simple linear regression. First of all, we need pairs of variables. So each pair can be called a case. Think about if we're looking for the relationship between the height and the weight of someone. We need pairs. We need a height and a weight pair that both come from the same person. If we're looking at the relationship between height and weight, then each observation of those two variables should come from the same case. Note that this was true in correlation. We kind of skipped over it a little bit because we were going to talk about it here. But this is true all across the board, that you need height and weight to be matched up, or you need your x variable and y variable to be matched up by their case. In general, we're going to be using the variable y, and I'm going to add the sub I to represent the ith value of the dependent variable. And I know we've already used some of these terms too, but you'll see me denote dependent variable as dv. Sometimes I'll call it the response, sometimes I'll call it the outcome. All of these are referring to the same variable, this variable where we're studying what happened. So for instance, in our previous example of the experiment, when I stuffed people full of ice cream and I wanted to see what happened, did they get attacked by sharks or not? That's the what happened. Well, y would be shark attacks. That would be what came out, or what was the outcome. That would be the response to having eaten ice cream. It would depend on whether or not someone had ice cream, presumably. So all of these are ways in which we describe this y variable. X is typically the variable that we use to denote the independent variable. So x is the ith, x sub I is the ith value, the independent variable, called the IV, the explanatory variable, because it explains what happened, or the predictor. So if it turned out that there was a relationship between ice cream and shark attacks, we would say that ice cream may predict whether or not you're going to be attacked by a shark. Usually, x and capital X for our random variable is easier to get data on than y. Not always true. In fact, this is just a pattern. I should say usually, I should say if you can only get data on one variable, x tends to be that variable, which is why we construct our variables in this way. Because if we're going to predict something, we want to predict a variable that's harder to get information on using a variable that's easier to get information on. This has been the start of our introduction to simple linear regression. In the next video, we'll move on to the theoretical model and start talking about some more of the properties of a simple linear regression statistical model.